can slowly start the presentation. Hello everyone, my name is Mikhail Ushakov, and today I would like to present you my research internship project about term rewriting systems with shared memory. In the modern world of software, we more and more encounter such an indispensable elements like web servers, databases, and operating systems. And many of implementations of these elements include concurrent algorithms and parallel sorting operations. And there exists one common concept which is very crucial for all of these elements, and this is shared data. So, because of the increasing complexity of systems, modern software systems, and the amounts of data that has to be processed, the concurrent algorithms become more and more fundamental. However, despite the fact that these algorithms give quite a lot of performance benefits, they also introduce a lot of extra complexity to the systems. Which means that concurrent software requires careful design and sometimes even formal reasoning. So, to deal with these kind of systems, we would like to have a formal framework which would allow us to, for instance, perform determination analysis, or check equivalence of two systems of algorithms, or in the end, generally allow us to do some formal verification of programs. So, but surprisingly, it feels like we already have an answer to this problem, and because term rewriting systems already allow us to do quite a lot of things like that. And we have an even stronger tool in our disposal, which are the logically constrained term rewriting systems. So yeah, it feels like this is the end, and our project can't really contribute anything interesting, unless it's not the case. Because unfortunately, traditional term rewriting systems lack direct support for shared mutable memory. Also, the existing approaches don't really consider a combination of parallel rewriting with shared memory operations. So, in the consequence, this all limits our possibilities to model concurrent algorithms and data structures using term rewriting rules. So we decided to formulate a research question of our project as follows. Can we extend term rewriting with explicit shared memory so that we'll get formal, implementable, and usable system that would allow us to model concurrent algorithms and data structures? So we created a small set of goals. First, we would like to introduce memory term rewriting systems as an extension of logically constrained term rewriting systems. We want to add explicit shared memory operations, and in the end, we also would like to assess the expressiveness and practicality of this approach through multiple experiments with shared algorithms and data structures. So, since none of you may remember or know what logically constrained term rewriting systems are, let's consider a small example. As a side note, I should say that logically constrained term rewriting systems, it's a computational paradigm that allows to express behavior of algorithms or systems using term rewriting rules, where each of the rules consists of a left-hand side, right-hand side, and an optional logical constraint. So on this slide, you can see a simple algorithm that allows us to compute the maximum over the linked lists of integers. So essentially what we do, we iterate over this list and compute the maximum. So the first argument corresponds to the current value of the maximum. When we reach the end of the list, we return that value. So let's look at the example. So the execution of programs represented using a term rewriting system is done by a reduction process. And the reduction process is essentially an iterative application of rewriting rules to some starting term. Let's see how it will work in this example. So we apply a couple of rules. We apply rule 1 because at each step the element in the node of the list is greater than the current value of the maximum. And in the end, we see that we managed to calculate that the maximum of this list of integers is 3. Very nice and simple example. So you already seen that we can represent data inside logically constrained generating systems. However, it gets more interesting when we start considering concurrent algorithms, because this data becomes local to the terms under rewriting. So whenever we work in a concurrent algorithm context, we have to manually deal with shared state synchronization, or for example, each update of the shared state would require us rebuilding the data representation. So we decided to simplify, to address this problem by extending the program configuration with an explicit memory function, where memory function is just a map from integers, partial map from integers to integers. Also, we defined a set of basic operations. So operation get, which allows us to read from memory, operation set, which allows to set values to the memory, and finally the atomic compare and swap operation, which I think nowadays is a standard assembly instruction, which allows us to verify the value at the memory cell, check if it equals to some expected value, and if it's not the case, we can set the new value to the memory cell. And this kind of operation, we use this kind of operation for synchronization primitives. You will see it later in my presentation.
Because it should be a catch-all where it goes to false.
Yes, I deliberately omitted that. So it goes to false if, for example, memory addresses are invalid. For example, it's not defined in our memory system. And in CAS also, there is a false case when value at x doesn't match with the expected value. But it was too much to put on one slide, so I just omitted that. Okay, also, because we are working with concurrent algorithms, we defined the notion of parallel reduction. Let's look at the small example. So we have this term with two operations where we try to concurrently update the memory map with two values. So in one step, we see that we nicely reach the final configuration where we set memory to the values. However, because we defined our parallel reduction as a combination of single-step reductions, it also raises some questions related to the nondeterminism. Because depending on how we would like to schedule these parallel reductions, we will have different final configurations. So assume we first decide to reduce the first subterm, and then the second subterm, then the memory function will store value 4. If we decide to do something different, then first we reduce the second subterm, reduce first subterm, and our memory will store another number. So such kind of we have to be aware of such kind of non-deterministic behavior of our systems while we design algorithms. Also, as traditional term rewriting systems, our memory TRS allows to deal with different reduction strategies. And reduction strategy is just a recipe of how we perform the reduction process. So, for example, in this case, we have this very simple term rewriting system, and we have this term, and because we are working under the innermost reduction, first we will consider the most innermost subterms. So after one reduction step, we will have a memory effect, and this way we reach the final state. However, if we consider the outermost reduction strategy, then it gets a bit more interesting, because we see that the outer term matches with the first rule, which means that we technically can rewrite it as a whole thing, which means that we omit the memory updating operation. So we have to be really aware of this kind of effects of different reduction strategies. So for example, in the algorithms we assessed during this research project, we deliberately decided to choose the innermost call by value reduction strategy because it gives us more defined and behavior which we basically expect more from programs. Yes, so the whole memory structure underwent quite a lot of changes. Initially we had this one cell with read and write operations, but unfortunately that was too limited to model realistic data structures. So then we decided to go with this memory array, but then we thought maybe we can define these memory operations as a theory symbols, which means we can use memory operations inside the rule constraints. So we thought it's a very nice idea when we can do that, for example, with a get operation. However, it becomes not very nice when we allow to have set operations inside the rule constraints, which means that testing the rule applicability can have a side effect of modifying the shared mutable memory. So, because specifying the semantic behavior of this kind of systems is impossible, we just decided to not go with this. And in the end, we just decided to use explicit memory reduction steps for each memory function. As a practical part of our research project, we developed an extension of the Cora. Cora is a term-generating analyzer tool developed by Cynthia Koch. And also to show some practicality of our system, we also created a small REPL which allows doing some experiments with memory term-generating systems. So, for example, we can include some existing TRSs, we can reduce symbols, examine the memory, and do a lot of other things. Yes, let's also talk a little bit about the implementation details of the parallel rewriting in Cora. So assume we have this term, also represented with this tree structure. So the process, the parallel reduction process is defined as follows. First, we find possible subterms which we would like to rewrite. After that, we try reducing the subterms in parallel using Java virtual threads. And after that, we collect the results and keep only the disjoint positions, because we don't want these two terms being reduced at the same step. This is a deliberate choice of the parallelism we wanted to implement in our system. And after that, yes, we can build the resulting term. So early implementation of the shared memory, which we created, was quite unsafe and inefficient because we didn't use thread-safe data structure. That was not a nice idea at first place. Then we had this idea, okay, we maybe can use a concurrent map and then allocate memory cells on demand. However, it proved to add too much overhead to our system. So in the end, we just decided to go with a compromise with atomic integer array, which became more predictable, but also much more efficient. Yes, also we had some problems with the parallel reduction implementation. We had to rerun algorithms a couple of times. Some of algorithms took more than 10 hours to run, so that was quite a lot of work. Also, it proved that virtual threads give us quite a big speed up in comparison with platform threads. Yeah. There is one more important thing to say, that all the experiments we have in this project reflect the core-based implementation, not only the abstract term rewriting model, which also gives its own implications on the results. And because we work with shared memory and shared data structures, we decided, why don't we create our own memory management system? So we decided to went with this very simple idea of shared memory without garbage collection. So we reserve first two cells in our memory for the next three memory address, and also the second is in something called allocation log. You will see what this allocation log is for. So let's consider this example when we try to allocate two integers on the heap in parallel. So what happens is that in one parallel, during the parallel reduction, one of the logical threads will try to acquire the control over the memory allocation system. So another thread will get stuck in the busy waiting loop until the first thread will finish. So we see that the first thread gets control over the allocation system.
What is the point why you need to put a cache in a loop? Because a cache is already atomic. So why do you need to put a cache in a loop? Because a cache is already atomic. So
because the allocation procedure consists of multiple steps. So we want to lock the whole system and allow performing multiple operations, such as fetching from the first cell, incrementing it, and so because it can't be done in one step.
So the whole allocation procedure is not just a cache.
No. So we fetch the memory cell, we increment it, we write it back.
So that is what cache goes to in a single step. Because cache takes a single step and goes to it all in one. So I'm not really sure why you need to lock.
Because if we fetch the value in concurrently, another cell will have old value.
Yeah, but cache goes in one single reduction step, right?
Only to the point when, yes, so the cache operation expects to work only on values, which means it doesn't work on expressions.
Okay, I'll come back to it.
Yeah. There were some deliberate choices. I experimented with different options, but yeah, that was important to do. So I think it's more of an implementation specifics of the engine at this point. So yes, so we managed to reserve the first cell. We free up the allocation system. Then the second thread gets access to the allocation system, and in the end we have this nice term with two addresses of integers allocated on the heap. Yes, so the shared memory idea made it possible to use arrays, matrices, and queues, and in general, expressing general algorithms with shared memory. However, it also made our model more explicit and I would say low level. As you see, we have to also reason about synchronization, evaluation order, all these allocations, which means that some of the algorithms we express with our system start looking closer to imperative programs than to functional rewriting algorithms. So this raises a question: can memory term rewriting systems keep this declarative strength of rewriting, or we are starting inventing some functional assembly? This question goes beyond the scope of our thesis, of our project, but still important to consider. Since we have the allocation system, we also can express some real data structures. And which one of those is the array data structure? It's very simple. Memory layout, we have the header with array size, and then n elements store the data. So yeah, if we consider this 10 element array, then we can also, this is how it can be represented inside the memory. And since we have arrays, the tradition of computer science also requires us to sort them. So we implemented a quicksort algorithm using this memory term rewriting systems. I won't get into the details of the implementation of the quicksort, but I can show you a nice animation of how the array can be sorted. Yeah, so since the important part of our project is to assess the practicality of memory term rewriting systems, we decided to benchmark our system and compare it with certain algorithm that can already be represented with in logically constrained term rewriting systems. So we found this idea of quicksort without memory on linked lists. And yeah, the idea is quite simple. So we have this list of integers. We take a pivot element, and then we split it in two sublists, where the first list consists of elements that are less than the pivot element, elements that are greater than the pivot are in the right call. So this way, we can sort a linked list with this kind of quick sort way. So then we decided to answer this question: can the memory really give us some practical benefits? So we compared implementations of two quick sort algorithms, one of those with memory and one of those without memory. And since both of these algorithms have the same runtime complexity, this will really show us how well memory helps us in practice. So we ran this algorithm for multiple input sizes, repeated algorithm 3 times for the more stable results. And so the first thing we did, we performed the wall clock performance assessment. And we already saw some interesting behavior of the algorithm inside the rewriting engine. So I would say after 64 elements, the performance of the quick sort algorithm became significantly worse than the memory version. And to the point when sorting 1024 elements with least quick sort took us about 30 minutes to perform the operation, which I think is not very acceptable. So we decided to look into the causes, into the roots of this problem, and we performed some profiling of the rewriting engine using the Java flight recorder. So we thought, okay, maybe the problem is with some, I don't know, object locations. So we considered the number of allocation samples that happen during the benchmarking, and we found that indeed the least version of the quicksort algorithm produces quite a lot of shortly lived objects. So then we have this thought, okay, if we have so many objects constructed, maybe it means that our memory management system of Java virtual machine is basically getting overloaded. So then we thought, okay, let's maybe look at GC pause time. And GC pause is an event inside the Java virtual machine when it stops the whole execution of the program and just does some cleaning processes. Generally, software engineers say that if we have these events happening in our program, it's not a nice sign. So we decided to assess that, and we saw that indeed, with big enough inputs, the least version of the quicksort algorithm has quite a long GC pause time, about 10 seconds for sorting 1024 elements, which is, yeah, basically it's 10 seconds of your runtime program does nothing, which, yes, okay. So then we thought maybe we can do the CPU time profiling to track down the core problems of the rewriting engine. And we found, so the CPU time profiling is another metric which allows to see at what threads and in what methods our program spends most of its runtime. So it turned out that for the least quick sort, majority of samples were actually generated on the main thread. And for the memory quick sort, the situation was opposite. Majority of work was done in virtual threads, which, as I said before, is really related to the parallel reduction procedure. Then we did this sanity check of checking the logical parallel reduction steps of both algorithms, and as you see, they have the same growth rate, asymptotic growth rate, meaning that the problem is not in our implementation, but rather in the underlying rewriting procedures. So as a summary, least quicksort works fast for small inputs, memory quicksort works better for large inputs. Yeah, they have the same asymptotic growth, and the main difference comes from engine level overhead. And I would say the main problem is that in least version of the quicksort algorithm, we store input inside terms. And the term rewriting engine has this idea of pre-processed subterms, and look which subterms can be reduced in call by value reduction. So if we store our input data inside the terms, which means that at each reduction step, we have to go linearly over each term, which takes quite a lot of work. But yeah, I should say that it's not really a problem of the engine itself, because the engine wasn't designed at the first place for the reduction. So it's also part of the future work. More interesting data structure. We constructed a concurrent queue. It is more interesting than the array. So the header of the queue consists of the capacity, so how much elements we can fit into the queue. Again, log value, it's done again for the parallel push and pop operations for the queue. And also we have current size and index of the form.
So this is circular buffer?
Yes, this is circular buffer structure. To have all operations of one.
And the log is just like a boolean that indicates whether the thing is logged or not?
Yes, whether some thread is performing an operation on the queue.
Okay.
Because these operations also, they are not one-step reduction. So, because we have concurrent queues, we decided to implement some more interesting algorithms, such as parallel breadth first search. And breadth first search algorithm is, I think most of you know what it is, just searching algorithm on a graph. Here we consider the node reachability flavor of this algorithm, when we just try to see what nodes are reachable from some starting node. So let's walk through our implementation. So first we allocate this array of visited nodes, where each index corresponds to whether a node is visited or not. And then we have two concurrent queues. So first concurrent queue works with the current layer, and the second concurrent queue allows us to add children to the next layer. So let's start. We put our starting node to the first layer queue, then we investigate the children of this node, and then when our queue is empty, we swap addresses of queues, so that second queue becomes the current layer queue, and the first empty queue becomes the next layer queue. What's also important, that the queue, so the layer elements of one layer are processed in parallel using parallel workers. Yeah, that's the main idea of this parallel breadth first search. And we have layer synchronization there. So yeah, let's also investigate some of the nodes of the second layer. So we finished with 3, and now we see that we already visited 1. We still have this edge in the graph, but we won't be examining 1 because we already visited it. Here we also use these CAS operations for synchronization. Done. Also, as well as graph, as well as the quicksort experiment, we decided to perform similar experiment for the breadth first search algorithm. So we implemented this breadth first search for logically constrained terminating systems. The differences of implementation is that graphs are stored like nested linked lists, arrays are stored as linked lists, queues are represented like linked lists, and most of our operations are linear because we work with linked list structures. And because we can't really perform synchronization in traditional logically constrained term rewriting, we work with sequential version of the algorithm. So yeah, we decided to compare these two encodings on randomly generated graphs from 1 node to 15 nodes, starting with vertex 0. Again, repeated algorithm 3 times for more stable results. And here is the results we got. So as you can see, the parallel version of the breadth first search algorithm takes significantly less parallel reduction steps than the sequential version. We can also see that in this projection from our graph. So small summary, the parallel breadth first search requires far fewer steps. For sparse graphs, we have some scheduling overhead because we work with parallel workers in the parallel version of the algorithm. The sequential version also grows much faster with dense graphs. And yeah, the main reason, as you can guess, is because all our iterations with data structures are linear, which is not very practical. So now I would like to, I think I convinced you that memory term-generated systems can allow us to model realistic shared memory algorithms and data structures. However, users of our system have to still think a lot about evaluation order, data races, the explicit synchronization. Also, during this project, we considered the idea of termination analysis. However, it's definitely not a direct extension of the methods developed for logically constrained term-generating systems. I explained we have all this scheduling, busy waiting, logs. All of these things complicate the whole meaning of termination of algorithms. Which means that in future, we would like to focus on abstractions on top of memory term-generating systems, and also some special analysis techniques. So let's go for the summary. This is our research question revisited. We introduced memory term-generating systems, formalized memory operations, analyzed the parallel reduction and side effects which it produced. We modeled concurrent algorithms and data structures and assessed them using different experiments. Also, finally, we implemented the system inside Cora and evaluated it for practical performance. Thank you very much, and I would like to answer your questions.